Hi, I'm Spencer Krause. I've been building robots for over 20 years. In that time, I've seen a lot of interesting things, and I've heard a lot of interesting stories. Collaborative with Spencer Krause is a place where my colleagues and I can relax, crack a drink, and talk about some of the crazier things we've seen at work and some of the experiences we've had that have gotten us to where we are today. Subscribe today to join the collaboration. Welcome to the Collaborative Podcast. I'm your host, Spencer Krause. Our guest today is Matt Travers. Matt is a CMU, Carnegie Mellon University Professor and a budding entrepreneur. Matt, welcome to the pod.
Hey, thank you, Spencer. Thank you for having me.
You're welcome. I'm also going to say I'm really proud to have somebody who's been on Neil deGrasse Tyson's podcast, Star Talk, on this podcast.
Thank you very much.
Clearly standing on the shoulders of giants.
It's during my life.
Yep. Awesome. So we were talking a little bit before we got started about sort of the importance of linear algebra in the robotics disciplines. And I don't know if you want to continue.
Starting off with a bang.
Something relatable to the average person.
Yes, that's right. Light Sunday afternoon chat. Yeah, I would say that in my experience, right, like linear algebra and understanding the Taylor expansion can get you pretty far. In the field of robotics, amongst other things. Yeah,
and I mean, I was saying I was the dumb idiot that took a master's in robotics without having had linear algebra as an undergrad, and I nearly didn't graduate.
Yeah, it turns out that like understanding linear algebra and understanding optimization is kind of a thing here in contemporary robotics.
Yep, yeah, for sure. No, completely agree. The thing was, like, I feel like when I was an undergrad, every professor told me that their thing was going to be super relevant to the rest of my life. So it was just hard to know which ones were lying, which ones were telling the truth. Turns out the linear algebra person was telling the truth.
Yeah, what do you think about the rest of them?
I don't know. I mean, I think like the business ethics person said that too, and it's not like I'm not a proponent of ethics in business, but I don't think it's something you can teach in a classroom. So that one kind of seemed a little bit more hokey. Like I think it's more like down to individual morals and philosophies and, not being a jerk effectively. But
yeah, fair enough.
You can't teach people in a classroom.
Yeah. Yes, vectors and values, I guess it would be
but that's
easier.
a lot more objective. Yeah, like you need right. that to make a robot work.
Yeah, certain aspects, certainly.
So, I mean, I guess expanding more on robotics, what are some of the robots you've worked on over the years that you're particularly proud of?
For me, it actually, first robot I'd say I really worked on, like outside of a mechatronics class or something like that, was the snake robots actually with Howie.
Cool.
Howie Choset. And in the biorobotics lab, and right when I first got to Carnegie Mellon before I was a professor, I was a postdoc with Howie, biorobotics back in sort of the perhaps, earlier days at the biorobotics lab when the focus was almost specifically on the snake robots. So when I was there, the guys who actually started Heavy, so this was before Heavy had started, and the very first series elastic actuated snake robot, the Sea Snake, was starting to be built. So before that, all of the snake robots had all been basically just hobby servos, really, really fancy hobby.
Like Dynamixels, effectively.
Yeah, they built their own. In fact, they started with, way back in the day, even before my time, they had started with Dynamixels, and they actually were hobby servos that they put together. Some of the early snake robots were referred to, I think, as like the Super Servo SS1. And anyway, so there's this whole lineage. They actually then, right before my time, had built sort of a very, very well engineered, they sort of built it from scratch. They made their own servos, very, very high end. They made all their own components, but it was still position controlled. So the way that they actually controlled the snake robot, they could do things like path shapes down its body, and they did all this work on gates, but they could never sense forces. You could a little bit, but there was never an explicit way to sense forces. So the hypothesis at the time was if we wanted to get the snake robots to actually act more like biological snakes in the sense that they could control positions and forces moving down their body, I was sort of at the very forefront of the hardware sort of catching up with the theory, on the biological theory, which was cool. So I started working at that time on doing sort of fancy force control methods. We called it like whole body force control. So it was happy to go into that. But
I'm kind of curious about it, to be honest.
it was this idea that you could. The way we thought about controlling the snake robots is the first, the mod snakes back in the day were 16 individual joints. And the way that you thought about controlling that robot was not one joint at a time. You thought about basically propagating, in many cases, like a wave down the body of the snake. So a spatial wave. So spatial.
I've heard about this. Okay.
Yeah, it's spatial and temporal. It's a waveform that moves down the body of the snake in space simultaneously as you're passing then a shape through the body of the snake. You're doing that temporally. So you call it like a wave equation, or what the hell do they call it? The serpenoid equation, which was effectively that. It just had a spatial and temporal component, and it would control the shape of the wave moving down the body of the snake, and then the frequency at which that shape would pass through the body of the snake, if you want to think about it that way. Yeah. So it was this way of like coupling the kinematics. So again, I thought about having one serpenoid equation and then parameters of the serpenoid equation, and that would tell me how to set the values that I wanted to track with each of my individual joints.
Yeah.
So the idea with the force control, not to go too far down the rabbit hole, was
I love rabbit holes.
If I think about, for example, there's like an amplitude of the wave that you're passing down the body of the snake. There's a spatial frequency, which controls the number of waves on the body at any one time. The idea was, instead of being like compliant in a joint, so like I exactly measure the force at one of the joints and try to do like closed loop force control directly on a joint. The idea was, could I be like compliant in the amplitude of the wave that was passing down the body of the snake robot? So for example, if I took the snake and held it stationary for a second and I pushed on it, you'd see the amplitude of the wave get larger. And if I pulled on it, you'd see the amplitude of the wave get smaller. Huh. And then if you took your hands off, it would
normalize.
Like a spring. So you're exactly programming in the physics of a spring, but in the amplitude of the wave that's traveling down the snake's body. So the idea here was like, if you look at a real snake, biological, not all snakes, there's caveats to any of this, but a certain class of snake, if you look at them interacting, for example, like there's a bunch of classic experiments putting snakes in, not classic, but experiments of putting snakes in pegboards. And you can see for different, and part of the idea this was some work that we were doing at the time with some folks. Dan Goldman was the name of the professor at Georgia Tech. Did all these like biological snake experiments, and the idea was, could we start to look at how the shapes, the kinematics of the snake, the real snakes, changed, and basically how they were like using the pegs, inhibiting, whatever, pushing off of them, were they avoiding some of the pegs? So it's pretty interesting. But what you see is that, like, in many cases, you do see the snake start to push off the pegs, but their shape stays constrained to still be in a wave. Huh. So the idea was, like, can you build the wave constraint in and still be compliant in the shapes that you're going to take on?
Because you have to be a little compliant, because the pegs aren't always going to be quantized the way that you were going to move as a snake to begin with.
Yeah, that's correct. But, like, if you just say, hey, I'm going to be compliant at every one of my individual joints, what you're going to end up seeing is the body of the snake will get itself like wrapped up in a knot, because you're not saying maintain the shape of a wave moving down your body. You have to do something extra to make sure that happens. So we built the constraint of having a wave on your body into the way that we thought about doing the force control, was sort of how we looked at it.
Cool. No, that's awesome. I mean, I've definitely heard about that I guess algorithm set. I don't know what I would call it, but like the fact that you could propagate a wave down a snake bot, and it seemed interesting. When you mentioned force, for some reason, I didn't think of it that way, because it always struck me as like position control, but that's awesome.
Yeah, it was a combination. So you want, there's this whole sort of theory by another guy named Henry Astley and others, but he was a postdoc with the folks at Georgia Tech, and he had a pretty good idea. It was a idea other people research. The reason we call it research and not search. So it was a biologist that had done these incredible studies of snakes. Henry at the time, Professor Astley now I guess, had looked at these earlier works and sort of had this interesting concept of the way in which, when we look at snakes and we saw them interacting with the pegs, whatever, that the shapes that we saw were actually the result of how the snakes ended up passing waves down their body. So the prevailing idea was that like on certain sections of the body, based on the fact that muscles pull, right? So the way that muscles work, if you pulled actively, there was going to be, if you put like a force acted on the body of the snake in the direction that complemented the way that the muscle was straining, it would admit the force. And if it was in the opposite direction, it would actually look like it was pushing off. So his whole theory was basically something that looked like us from observing from a world view or whatever, a global view, looked like the snake was doing something very complicated enough. Force and position control was actually just a passive function of the way that the muscle activation actually happened.
So there wasn't even intent behind it. It's just
it was coupled to the kinematics a little bit. Yeah, it was passive. It changed along the body of the snake as a function of time, so it looked like it was dynamic. But again, his theory was that like all of the complicated stuff that we saw was just a passive way that the environment interacted with the body of the snake based on the muscle activation, which is pretty cool.
That is pretty cool.
So anyway, yeah, we can geek out about snakes, but that was sort of for me, the beginning of actually working on a real robot. So things I had done previous to that, my PhD was focusing on tracking satellites. So doing a lot of state estimation, a lot of more data manipulation, and
totally different thing.
Totally different thing. But it was still control systems. It was still state estimation. So still doing optimization to try to get systems to be more automated. Was sort of the common theme. So yeah, it was that, and then those actuators. Then Heavy, they can tell obviously their own story, but
I haven't had Bob and Dave on yet.
They're cool. They're great guys. But that was I don't think they would say that was the beginning of Heavy. They would say that was the first series elastic actuator. At least it was within biorobotics. Once they sort of went out and formed Heavy, they created an entirely new actuator. The common theme between them is that they had the series elastic element in them.
Yeah, that's really cool.
Yeah.
I feel like there's I don't know, not to go too far down another rabbit hole, but on the series elastic thing, there's different schools of thought on how stiff your spring should be.
Yeah.
You don't have to go there if you don't want. It's kind of nerdy.
It's an age-old question. Yeah. Well, maybe not age-old, but it's a question that gets talked about.
Decades-old question.
Yeah. And do you do it with metal springs? Do you do it with natural rubber? Of course, the Heavy folks went with rubber. So yeah, a lot of thought has been put into that one. I know Rob Ambrose, who's down Texas A&M, is sort of big, father, whatever, very instrumental in putting SEAs in lots of different robots at NASA.
Yeah, they tend to use stiffer springs in those ones, is my understanding.
Yeah, that's right. So it depends. At the end of the day, it depends on the fidelity that you actually need in your force control, and it depends on the dynamic range that you ultimately need. So if you know that you're going to experience, really small forces over short periods of time, using a really stiff spring and with, that's super high fidelity, it is going to work for you really, really well. Depending on how wide, the spectrum of different forces that you want to be able to accurately sense, it gets very difficult.
Yeah, well, it depends what you're doing. One of my friends, his name's Anton. We were in the Carnegie Mellon Robotics Club together. Made a book scanning robot. So it was actually more complicated than it sounds. He opened the book at he had 90 degrees. So one page was at back 45, the other one he had two cameras mounted DSLRs, and then he had little UHMW peg that would come in and turn a page, and then to get the page splayed out so the peg could insert. He had this finger that was had a series elastic actuator on it it was this rubber thing, and then it would kind of turn the page. And that one had a really loose spring, and it needed to work correctly.
Yeah, that's pretty cool.
The way it was designed. Yeah.
Yeah, you can you could have this conversation with engineers forever. So yeah, it depends on the application. I don't know of one thing that just works for everything.
I think that's why it's fun.
Yeah, no, I've seen just in how to stick a spring in a really small place and be able to measure deflection around it. I've seen some incredible engineering solutions. Certainly with the Heavy folks, certainly with the A&M folks, and Yeah, no, it's, again, if you understand the problem, I think you can probably figure it out. It's just like how far do you want to actually go down that route?
Did you know that Collaborative with Spencer Krause now has a merch store? Please go to cwskmerch.com for the latest in CWSK styles. We've got hoodies, t-shirts, hell, we've even got whiskey glasses. Everything in the store has custom art that our team worked really, really hard on, so go ahead and show your support for them, me, and the rest of the CWSK team by going to cwskmerch.com today. Better yet, support yourself and use discount code PODCAST10, all one word, all uppercase, for 10% off your entire order. Thanks for your support and enjoy the rest of the show. Collaborative with Spencer Krause is sponsored by SKA Robotics. If you're in the market for elite field robotics expertise, please consider hiring SKA Robotics. They sponsor this podcast and solve some of the toughest engineering problems in the world. SKA Robotics can be found at skarobotics.com.
But yeah, so then it was past the snakes. They actually started, they produced a second series elastic actuated robot that was affectionately called the Snake Monster.
I don't know this one.
It's a hexapod that had, originally, the very first one had the same modules, red modules that were in the first series
elastic. Was this the big one that was in the FRC for a while, Field Robotics?
That was, that was a later one. Okay. So there was a smaller scale one. It was probably about a meter-ish wide.
Okay. So that's the diameter of the base, or like with the legs?
Yeah, with the legs split out. So it was normal posture of a hexapod. Excuse me. So I forget what, there's a specific name for it. But what you'd imagine if you started hexapod. So front legs, middle legs, back legs, all in a row.
Yeah.
And then into a central box, and then that. Again, the legs were made out of the exact same modules that were for the first series elastic actuated.
Snake Monster.
Correct. Yeah. Yes, the naming conventions.
Also known as hexapod.
Yeah, that's right. So yeah, that was the first, as you're alluding, the first of many hexapods. But I also did some work more on the neural control. We started effectively talking about it. So there's.
What do you mean by neural control in that context?
In some sense, and this is, I'm sure you'd find someone who would argue with me over this, but in a way, the way that we thought about the serpenoid equation that I was talking about earlier, there's another school of thought. These folks who focus specifically on things called central pattern generators, and part of the idea there is that even in our nervous system, there are neural oscillators that for example, your walking gait. Why can you, some of us can walk and chew gum at the same time. So the idea is in a sense, is there parallelization going on where you still have cognitive function over your legs, but you're basically using a feed forward oscillating pattern to tell you how to activate your muscles. So there's lots of evidence, people who study this for biological systems, and it turns out that in a sense, the serpenoid equation was not a generalization, but a specific example, perhaps, of a CPG.
Oh, that's interesting. So it's the kind of stuff your cerebellum does.
I think. Sounds right to me. I'm not that.
Remember high school bio?
Yeah, I'm not actually that smart, but the neural oscillator part I remember. But anyway, so with the snakes, we were never doing explicit CPG stuff. I wasn't, but it was close enough that when we started working on the hexapods, there wasn't an explicit gate equation for the hexapods, but they still operate in gates. So the idea was, can I start to take some of the ideas via the force control for the snakes and start to basically implement that on the snake monster? So similar ideas where I want to think about doing force control around a gate, where the gate is defined as time varying kinematics of the system.
Oh, that's interesting. Did you find there was common code you could use from the the serpenoid work you'd done? Or?
Yeah, it was a similar idea that I talked about earlier. Being compliant in the amplitude of the wave that you're sending down the body of the snake. You could do a similar idea where with the hexapod robot, how big
of a step do you want?
Yeah, that's correct.
How high up do you want your feet to go?
Yeah, so it's a parameterized gate
what's
equation.
Your frequency?
That's exactly correct. So you could be All of those parameters you can now build into a function that controls the kinematics of your system. If you can then measure forces at all of your joints, this was the entire idea, you could then determine how to be compliant directly in those parameters, as opposed to be like compliant around this position on an individual joint. So you could be compliant within a gate, was the whole entire idea.
That makes a lot of sense.
So, thank you.
Yeah,
My work here is done.
I mean, there's going to be like a rock or something, right? Like that's the whole point of having legs, is to be able to deal with weird environments that aren't necessarily flat and easy to contend with.
Yeah, and you can think it almost as like, if you're walking along a rocky surface, you're trying to avoid or trying to, leverage what you can in the environment, but like all of a sudden a rock underneath your foot, suddenly moves. A lot of that's going to be reactive and a lot of that's going to be force-based. But like the way in which it has to be a very large disturbance for you to like change the way that you're actually walking or to stop or to like have to go into recovery. So it's a similar idea, which is again, like, can I preserve the overall motion of the system to a certain extent, but give it enough compliance in the correct directions that it doesn't start to take away from what I'm trying to do with my locomotion.
Yeah, that makes a lot of sense.
That was it.
I feel like I wish I had you as a professor when I was in school.
There's one. Those were the first several robots, and in fact, the snake monster and some of the work that you saw with the larger robots actually led then into a couple different projects that I started working on with DARPA, which is sort of a jump, I guess, but the direction I was sort of moving in with the first platforms, Snake Monster, was starting to incorporate more autonomy onto those systems. To, the snakes, for example, back in the day, the mod snakes when I first got there were completely, it was a controller, and a person was acting as the intelligence for the robot.
Yeah.
So starting to think about how we could start to add higher level reasoning, perception directly onto those systems was, kind of where my interest laid. And
that was you on the Jimmy Fallon show with Howie.
It was me. Yes, my claim to fame. That was the mod snake. That was before the sea snake. There's sort of a funny story there, which is that that robot was a serial chain, again, 16 motors in a row, but each one of the individual connections, if you've ever worked with serial communication, and worked with things that have lots of connectors and trying to send the serial communication through the connectors.
Propagating failure if you lose one.
Yeah, exactly. Each individual one of the joints in that robot was held together by 4 screws. But you had to undo the screws to do any of the mods or do any maintenance on it. So you couldn't like Loctite the screws. You had to take the screws in and out. So inevitably the screws, it's a snake robot bouncing around on the ground, inevitably the screws would come loose. You'd start to get intermittent electrical communication. So the camera was on the front of the snake.
Oh no.
The camera image on a good day that you could actually get back at like the base station, it was completely wired at the time, but the main points of failure were the 16 connectors or whatever, 16 plus 1 or something. So the day of the Fallon show, one of the things that would happen is if you left the robot on for a while, the video would just cut out. Like it's just whatever, totally non-deterministic. So we had to go and like there's hours of prep and we're there all day and like, it's a 15, whatever, tops 2 minute bit, whatever, where how it was going on. But they again, there was 2 days of prep. There was a lot of stuff that went on just for this, which, God bless their producers, because they're doing a very good job.
Awesome.
So the level of preparation, I guess it's a pretty big television show, but the level of preparation was very nice.
2 minute bit. Yeah. That's crazy when you think about just the amount of work that goes into
weeks. Weeks before getting the getting the things together, finding the people. It's a lot of work. So, anyway, the snake, we get there. I met Questlove. I didn't really meet Questlove. I was standing next to him, and I went, "Hey, Questlove."
That's awesome. Well, you get to say hi to Questlove.
I did say hi to Questlove. It wasn't that cool, but so the snake is on, and the producers like, all right, we do a rehearsal with Jimmy Fallon, let him know. So the snake is supposed to wrap around Jimmy Fallon's leg and climb up his leg. So Howie comes out with the snake and puts it down. We know we've done this a million times, so we put it down in like a position. It's like easy to climb his leg. And
Has Fallon rehearsed it yet, or is this his first time?
Yeah, it was kind of weird because it actually wraps around it constricts around your leg, and it uses the friction of being around your leg to climb. If you've never felt a snake robot on your leg before, it is a little bit creepy. It is a little bit weird. So anyway, yes, we did rehearse with him, but then we go and it's live. I mean, there's a studio audience, and Howie picks up the snake and goes to walk out on stage. And the producer's standing next to me, and I have the feed from the front camera of the snake. And he's walking out, and I go, the camera's dead. What? To the producer. And he goes, what do you do? And I was like, the only thing that you can do is power cycle the robot and bring it back up. And he just looked at me and goes, do it. So it's a big red button on the case. So I pop the button, and the snake goes limp in Howie's hands as he's walking out on the stage. He didn't even know. I told him after. He noticed that the snake went limp when I told him after, but he didn't connect the dots of anything that was happening.
Wasn't even thinking about it. He was too much prepping for the bit.
So I mean, it's pretty nerve-wracking.
Sure,
I don't care.
Millions of TV viewers. Yeah.
I don't care. How he's done. Lots of large presentations and that. But like, I don't care who you are. The first time I think you'd go on the Fallon show, you'd be like, a little starstruck. Sure. Anyway, so power cycle the snake. And it comes back up, literally. Boom. The video is there, comes back on. He puts it down, we climb. And during the rehearsals, it's actually kind of hard. The snake, once it's wrapped around, you can like pop its head and like look around. It used to be for you could climb like a telephone pole with the snake, and then you could like take the camera and maneuver it around. So sure enough, we wrap around his leg. I hit the thing for the head. The head pops out. And I just got it perfect where it looked directly up at Fallon, and he waves down at the camera. It was like we rehearsed it, I swear to God. But yeah, it was the one time during any of the takes that like I actually got the camera to look at him. He waved at it, climbed back down his leg, and that was the day. We're just like,
that's awesome.
All right. Yeah.
Ship it.
Yeah, absolutely. 100% true story. That pretty much.
Yeah, that's super cool. I did not know you were the guy controlling that until you told me about that the other day.
My claim to fame, one of them. The producer was literally standing there next to me. He watched the entire thing happen. When it got done, he literally just like patted my back, walked away. There was one time we had the snake monster, and we had the snake robots, and we were going to the summer Davos, to the World Economic Forum. So Davos is the World Economic Forum. Summer Davos is, I guess, every year in Tianjin. So we got
every year in Tianjin.
Oh,
Tianjin.
Tianjin.
Okay.
No, don't worry about it. So I was like amazed. It's like a city. I think it's bigger than Chicago. I'd like never ever heard of it, which I guess tells you something about like the sizes of cities and how many of them.
I'm just now hearing about it. I feel bad.
Yeah, it's gigantic. It's a very large city. It's a port city.
Where is it? Like what country?
Tianjin, China.
Oh, okay, got it. Yeah.
But so don't ask me. I don't. More than the fact that that is where Summer Davos is. I don't really know very much about it. But what I do know is we got Carnegie Mellon. He got asked, and Howie got asked to go and like demo the actual robots. So we had like a booth, effectively, and he's like, I want to go to China. I was like, all right, cool, definitely. Let's go control some robots in China. So there was a pre-trip to that trip, and it was somewhere else in China. It was without me. It was with one of the other graduate students. And by the time multiple robots traveling around China, and we get the snake monster finally to the booth at the World Economic Forum. We go to turn it on, and it's absolutely nothing will come. Absolutely nothing will come up. And like, the number of emails and the number of it's a walking robot that we brought to China. It's like imagine how difficult that was. Sure. Put it in a case to get these people to approve to get it into the World Economic Forum. It was a lot of stuff went into getting this robot.
I'm guessing
there.
It was hard to access the source code to.
It's me and a graduate student. I'm basically worthless. And the grad student didn't build. It's not like you know, I'm gonna go in and do like full open heart robot surgery, and it's not like you can like call an engineer, like whatever. Google doesn't exactly work, so it was a very unique scenario in which we figured out that we could like bypass the internal switch, so we had to like go to the equivalent of like a Best Buy and like buy a router and actually like wound the World Economic Forum. People gave us like a 200-foot EtherCAT cable, and we had
200 foot.
it was just like we were like, get us the longest one you can find. They're like, this is China, like anything is possible. So we got like a very, very long, and like actually had to duct tape the additional wire to the tether. There was like a router sitting on the back of this thing. It was actually duct taped. But this was, in terms of making a robot work in a foreign country with very little actual knowledge, I can tell you that robot worked. There was a lot of tape on it. But if we're telling robot glory stories, this is definitely
How
one
far
of
in
them.
advance of the conference did you find out that you had to perform this repair?
It was in the booth.
Okay, so it was going on. Like,
it was-
you guys were doing this in front of an audience
Well,
while
it-
like, there were
It was like behind a counter, and we had translators.
crowds of Chinese people walking by being like, you know.
We had translators, but like multiple translators were just in the booth, and the translators are like looking at us like, oh my God. I'm like, oh God, we got the worst booth.
The kind of stuff we did when I was in BattleBots, but like.
Oh yeah, just at a much scarier level. I like, the number of like CEOs and just major corporations.
Seriously?
Like, yeah, I mean, summer Davos. So yeah, it was quite a crowd. But the robots
and
did
you were
work.
able to still get it going under that kind of pressure.
It was awesome. There was like
Yeah.
other like, I don't know, there was like a humanoid, one of the first companies that was like producing human. This is like but pre-COVID. So this is years ago. And there was like everything else is like very well done and all these like immaculate booths. And we had this like robot literally with like a router taped to its butt and like a wire like wrapped in electrical tape with a Cat 5 sticking out. But it
ran.
It did. It moved. So yeah, that's all that matters in the end, I guess.
Yeah. I remember there was some component where you had like radios that were like getting dropped, so you had a mechatronic that had to drop the radios, and then you had a drone involved in some capacity, if I'm remembering right.
Yeah, that's correct.
Was there a dog in that too?
Yeah.
Like, okay, so you had a robot dog also.
The Spot robots.
Yeah. Got to shoehorn one of those in that time period.
Oh God. Yeah, it was. Yeah, there's a million stories from that. With the dogs or the quadrupeds in general. Trust me when I tell you, stairs were made for legs. There was a numerous lessons learned on Sub T. The comms part of it. Oh my God, robot communications. Let me tell you something.
You were probably using something off the shelf like a.
We did use. I don't know if I can comment about that directly.
Fair enough.
But yes, we did use something off.
I'll beep out the brand I said.
We did use something off the shelf. We actually when we first started, we started with Ubiquiti nodes, like repeaters that you get. Speaking of Best Buy, so we actually went to Best Buy and got like wireless, nodes that you put up in your house to like extend the range of your internet. So it was inexpensive. They were easy to get, but I'll tell you, there's a lot of things going on with communications where if you don't know what you're doing, it's very easy to go in the wrong direction. So for example, with the Ubiquiti nodes, they do this remeshing. So like when you put the nodes up, the way that they actually form their own like network topology is they'll sort of understand signal strength, and they do a remeshing. Okay. But there's like an underneath.
So that's a state they have to like go into to do that. So they're not dynamically doing it on the fly all the time.
Which makes sense. Like if you put it up in your house one time and whatever, like yes, you want your network to be optimized, and it's a pretty simple thing for them to do. However, if you stick these nodes on repeaters like we did, so we did drop them. We put them like in cases and dropped them out of the back of the robot. But then we also had Ubiquiti nodes on the robots to talk to the rest of the network. However, if you now have nodes that drive around your other nodes, it just constantly tries to re-optimize the network. And there's like a 30-second latency or whatever. I don't even know what the actual latency is.
But it just takes down your network, basically.
100%. And with a grain of salt, to be honest, that's what it looks like. That's what we thought was going on. Who knows what was actually going on underneath? So it was like trying to hack what was going on, trying to understand. But it was miserable. It was really, really miserable. And as you added more nodes, the problem got worse as you added more robots. Yeah, it was pretty bad. So we ended up, I think it was Doodle Labs, I want to say, is another sort of person who's in this space. I think it was Doodle. They make the radios for like when you're looking at the NFL and you see coaches like get on their radio.
Yeah.
Like that, I would think was their claim to fame.
That's interesting. So like just the ability to operate in an environment with like, 100,000 cell phones or whatever.
Yeah. Yes. So they had like a more protected and they had like better meshing. And they're sort of like a mid-level, who knows exactly, but they're sort of super duper high end, which is like what the like real DoD folks actually use. And those are, very expensive per unit, multiple thousands of dollars per unit. The ubiquities were multiple hundreds of dollars per unit. And there's sort of,
Which still feels expensive if you're a grad student.
It is 100%. It is very, very expensive. I'll say we were one of the funded teams for Sub-T. So, it was not an exorbitant amount of money, but it was, enough money that you could actually build robots. You could buy radios. So, anyway, we switched up our radio thing. It was a thing that we were even into the very end of that project we're dealing with. It is very, very challenging to take lots of data far away in a place that has challenging communications and to get that information back to anywhere you would want it to be.
Yeah, agreed. I mean, there's a reason why those radios are like, thousands and thousands of dollars each. It's because, it's like to your point, it's not easy to do that.
Yeah, like streaming HD video from, several miles down a mine.
Oh, wild.
Yeah. For example, full point clouds, or not full point clouds, but, sampled down point clouds. You want video. Most of the robots will have multiple different cameras. You want to be able to change from the cameras. So, yeah, it was a very, very challenging thing. Anyways, there was many, many, many lessons learned on that project.
That's awesome. We could do a whole other podcast just on that.
Yeah, you really could. But yeah, like you said, it was drones, walking robots, ground vehicles. I think during the final competition, we had 10-ish robots.
Like 10 different types of robots?
We had three drones that we constructed that were custom. Two of them were on the back of two of the ground vehicles. There's a third of those. There was 2 Canary drones. Canary was a company that was started by several folks who were on the team. In fact, Jay, who works at Hellbender now, cool. Did the Canaries. So there was 2 Canaries. There's a Spot robot and then 3 ground vehicles. So I guess there was 9 total robots that we brought with us.
That's wild.
It was insane. But yeah, for what it was we tried to do a lot with what we had.
Yeah, it sounds like it. That's insane.
So yeah, there was the story about the Spot robots is actually interesting. So there was these circuit events. It was I think it was during COVID, or like right after COVID. It was like the first thing that anyone got let out to do, but because it was like whatever of national defense, they were like, all right, you guys are greenlit. You're gonna like start the world back again or something like it. So we ended up going to this place south of Seattle, which is close to, you drive through the city where Kurt Cobain was born.
Oh, cool.
And I bring this up because if you saw this place, not to make anyone angry, if you saw this place and you described it as the place where Kurt Cobain grew up, you'd be like, that makes sense. So it was a couple hours, nice place overall, but you'd understand if you were there. And it was at the competition for DARPA was at this never commissioned nuclear power facility.
Oh, cool.
It was pretty cool. It was like very horror movie. It was like up on a hill, like classic, like Simpsons stack, like cooling stacks, and very picturesque.
Was it like set to be commissioned, or was it like never going to be commissioned?
It was set to be commissioned. I believe it was called SATSOP. I could never remember what that actually stands for. I think that was the name of it. But they had like built the entire facility, and we're about to bring it online. And like the residents, this was the story I think they had told us. It's like people there were like, we don't want a nuclear power facility here, so it like got everything up to like getting fueled. And they pulled the plug.
So it's never getting commissioned. Like that's just a landmark.
Oh yeah. So anyway, that was where they rented. It was the urban competition. It was there's a lot of vertical up and down.
It must have been so much money just to get that thing. Okay.
Oh my god. Yes. So we had spent. Back to my comment about stairs are made for legs, but. We had spent like a ridiculous amount of money and time trying to modify wheels. We had 3 conventional ground vehicles, electric ground vehicles that we built. We had spent an exorbitant amount of time trying to modify wheels to get those vehicles to go up and down stairs.
Right.
Way harder than you might think. I mean, we were burning money left and right. So we finally like came up with this like go down backwards and put steel plates on it, but like we had a 400-pound robot that we tried to put downstairs backwards, and we manually drove it downstairs one step at a time, rocking. It was so dangerous.
Brutal.
So we flipped it in the competition. We flipped the 400, and it had the drone on the back of it.
So you crushed the drone.
The drone was a little bit crushed, but everything was, I think, still operational. I think the drone needed cosmetics, but it was still actually operational.
Nice.
It actually, the slam, I believe, don't quote me on this, I guess it doesn't matter at this point, but the slam, I think, actually didn't go unstable in the flip. Like when it actually landed at the bottom of the...
Like it knew where it was.
Yeah, so the map, it was actually stable in the map. There might have been some drift in it, but
that's pretty cool.
It was pretty cool. But JPL, or the JPL folks at the time, I guess that now sort of evolved into the Scale AI folks, or no, Field AI, excuse me. They showed up with the original. So it was the first time anyone in that competition had seen the Boston Dynamics spots, like outside of like a video, like a YouTube video.
Yeah.
And the JPL people showed up with the spots, didn't tell anyone that they had the legged robots.
Yeah.
And the entire place was like stairs up and down. So anyway, they like dominated the entire competition because they had the only robots that could actually successfully.
And they like were able to keep a secret, so nobody else tried to.
Well, like the BDI people like showed up with them, and like everyone was sort of like miffed. Like, what the hell, you know? So anyway, long story short, everyone got spots who could, who could.
And
everyone.
That's why that's always used with stairs now, is because they just crack that.
Oh, they're awesome. I mean, those robots, of any robot that I've certainly ever bought and worked with in my life, like those robots are so sweet. Like they are really, really, there are numerous things about them that are incredible.
That's awesome.
Yeah, it's really cool.
So I gotta write a proposal. I guess I overstacked my Sunday, but it has been an absolute pleasure having you on. Is there anything you want to plug, or like a kind of a message you want to leave for listeners on the way out of this?
Just so new endeavor on roboLoop, as you know about it, a company that I'm starting, or have started with my partner, Ned Eldridge, and we are spinning up. It's a robotics for electronic waste company. We operate out of Export, PA, and we're operating out of State College, PA. Right now, and come check us out. We're sort of in a growth stage right now, getting our first robots in, but we're really excited about what we're doing there. And website is roboloop.net. Come check us out.
Awesome. Matt, thank you so much for coming on.
You got it. Absolutely. Thank you for having me.
A pleasure.
Thanks for joining us today. If you've made it this far, chances are you'll like other episodes too. Collaborative with Spencer Krause can be found on YouTube, Google Podcasts, Spotify, Apple Podcasts, Pocket Casts, and Radio Public. Subscribe today to get notified when the latest episodes release, and support the channel. Have an idea for a guest I should interview? Hop in the comments and let me know who that is. I'm always looking for new people to talk to, and chances are you know folks that I don't yet. Thanks for coming in, and I'll see you on the next one. Collaborative with Spencer Krause is sponsored by SKA Robotics. If you're in the market for elite field robotics expertise, please consider hiring SKA Robotics. They sponsor this podcast and solve some of the toughest engineering problems in the world. SKA Robotics can be found at skarobotics.com.